My name is Jesse Vela. I'm a computer science student at University of Houston, and my ORU summer project is on material informatics applied to high-entropy alloys. The motivation behind much of the data science and material informatics being conducted today is the Materials Genome Initiative. The goal of the MGI is to accelerate the discovery, development, and deployment of new materials. The MGI was created in 2011 in a time when artificial intelligence was advanced, but not as advanced as it is in 2023. With the rapid development of machine learning, big data, and big compute power, MGI initiatives only become more important. And there are 5 aspects of the MGI, and as conducting a lot of experiments, properly storing data and knowledge, conducting advanced simulation, conducting materials informatics, and advanced statistical analysis, and materials design. So we've been doing material informatics on high-entropy alloys. High-entropy alloys seem to be very popular at the moment, but the large number of potential high-entropy alloys make it a difficult class of materials to study because the metals can be so varied. Because high-entropy alloys can vary so much in composition, there is a lot of opportunity to design HEAs with tailored properties. The largest publicly available dataset of HEAs was compiled by Borg et al. And here is a brief overview of the information in the Borg database. There are 745 single-phase entries, and there are 669 multi-phase entries. Regarding crystal structure, there are 468 body-centered cubic entries, and there are 265 phase-centered cubic entries. The remaining 812 entries are either multi-phase or of some single-phase form besides BCC and FCC. We've chosen to mainly focus on the 745 single-phase and specifically the 468 BCC alloys. This is because due to ongoing projects in the group, resources were available for more work to be done on BCC alloys. Here's the elemental co-occurrence network, showcasing how elements are alloyed together, specifically for the single-phase BCC alloys. The dataset is richest in niobium and titanium, followed by the rest of the refractory elements. The refractory elements are most often alloyed together due to the fact that we are looking at BCC alloys, and refractory elements are typically BCC formers. We see that hardness and yield strength are both captured together and separately for each alloy, with more yield strength entries being captured in total. And in graph C, we see how frequently an element appears at a certain concentration in the database. We see that most elements appear in alloys are at around 20%. This indicates that most alloys are near equimolar, and in D we see the distribution in hardness and yield strength. Given the data in the Borg dataset, the goal of the project is to create a multi-information source model that can be used to better optimize for yield strength. A popular surrogate model for Bayesian optimization is the Gaussian process regressor. This is because GPs natively provide a prediction and plus or minus uncertainty bound on that prediction. Gaussian processes provide plus or minus uncertainty bound as the model is a distribution of functions, and we take the mean of this distribution as our prediction, utilizing the variance in the distribution for our uncertainty. In this work, we will use hierarchical Gaussian processes in order to use hardness as a cheap proxy experiment for both yield strength and fracture strain, and we can propagate the uncertainty of the GPs by sampling from the distribution of functions directly multiple times and then averaging out the second GP. In this toy example, we are adding points to a cheap proxy experiment and continuously sampling functions from the cheap proxy to plug into our expensive truth experiment. The expensive truth function only has a set number of experiments, but we are allowing the cheap proxy to gather more data. We see that as we add data points to the cheap experiment, the model becomes more accurate, making the expensive experiment more accurate, even though we are not increasing the number of data points that it is seeing. The purple line is one of the many functions generated by the proxy GP. The truth GP here is trained with the red points evaluated on the purple function as an extra input. This is repeated for many samples, and the truth GP is recorded for each. Here we see one of the benefits of propagating uncertainty and utilizing chain GPUs. We see that adding experiments to the proxy experiment in the same input space reduces the uncertainty of values in the truth GP. We see that in regions with queries in both the truth and proxy, uncertainty is substantially lower than in regions with only truth queries. These are the features used in the GP regressors. Regarding relevant features for hardness, yield strength, and elongation, we have queried commonly used properties for modeling solid solutions, strengthening, and their statistics. For example, we consider the rule of mixture average, we consider the compositionally weighted average property differences, and maximum compositionally weighted average property differences. We selected these features by calculating the mutual information for each feature against each target, taking the highest mutual information features. Mutual information is a number that explains how much one feature changes as another changes. Here's the model for hardness. This is the first model that is fed into the subsequent GPs for its accuracy in predicting hardness. For hardness in each subsequent GP, 3 folds were used for cross-validation, and temperature series entries were restricted from being split into the test and train splits. The R&K value is the Spearman rank. The value is how well it ranks the values, 1 being the perfect rank, and -1 being the perfect inverse rank. We also have the mean absolute error, the root mean squared error, and the R-squared value. We see very high R&K and R-squared values, as well as low mean absolute errors and root mean squared errors, indicating a very good fit for hardness. Here we see the yield strength model control and the hierarchical GP starting with the hardness model propagated into the yield strength model. We see that there are very few differences in the control model and the propagated model. We do note that the mean absolute error and the root mean squared error is slightly higher on the yield strength model, or in the hardness into yield strength model. This is likely due to the fact that we are only using room temperature hardness experimental data, which conflicts with the temperature sensitive yield strength feature. We see quite good results in our fraction strain control model though. Hardness to fracture strain performed much better than hardness to yield strength, increasing the metric substantially compared to the already good control. Our control model had an R&K of 0.87 and R squared of 0.76, as well as relatively low mean absolute errors and root mean squared errors. The hardness into fracture strain model, on the other hand, has an R&K of 0.9 and an R squared of 0.82, with substantially lower mean absolute error and root mean squared error metrics. Here we utilized both the sample feature from hardness and yield strength together in a hierarchical GP into fracture strain. We see that the model underperforms compared to the fracture strain control, and this is likely due to the fact that the hardness into yield strength model itself underperforms, introducing a lot of noise into the generated feature, not being very representative of an actual yield strength feature. Here is the same model, except that we are also propagating the hardness feature directly into fracture strain, as well as propagating the yield strength feature that is generated from the hardness feature into fracture strain. We see that the metrics improve a very slight bit, but not enough to really compare it to the control model, let alone the hardness into fracture strain hierarchical GP. We've also been researching the use of multitask GPs for our dataset. Multitask GPs are another form of Gaussian process regressor, and they use the same training set to train multiple target features at the same time, which allows the model to gain information about both target features and influence them. For our case, something like hardness and yield strength are known to be correlated, so we would like to train them at the same time because we know that those two are actually related. We've been using the package GPFlow in Python, and primarily utilizing the co-regionalization kernel that comes with GPFlow that wraps over a standard Gaussian process kernel. The co-regionalization kernel allows us to utilize a training set that has entries in either both target values or only one target value, drastically increasing the size of the training set. Here are the results of using a co-regional kernel on the dataset for hardness and yield strength. We unfortunately see very poor results. Utilizing toy data gave us the expected great fit, indicating that the code is performing as expected, but the dataset is just providing poor results. This indicates that the limited features, the size of the dataset, and the further size reduction of that dataset through the forced intersection of feature selection makes multi-target modeling difficult for the dataset. GPFlow offers great kernel manipulation support, which is promising for optimizing the kernel to hopefully see improved results. For future work, the Borg dataset can hopefully be featurized even more to discover features that have high importance in predicting hardness, yield strength, and fracture strain. There are also plans to continue manipulating the kernels and bounds provided in GPFlow to provide acceptable results when conducting multitask modeling. Utilizing kernels that handle categorical features is also important. Currently, we are utilizing some categorical features, but the kernels don't gracefully support them well, as one-hot encoding increases dimensionality, which is very undesirable for Gaussian process regressors, and label encoding enforces a hierarchy that is not necessarily representative of the categories.